Okay, folks. All right, how we doing? So this, I think, will probably be the last lecture I record on this week 10. I think we can do this in one lecture. So again, in a previous semester, I would have spent a lot more time on equilibrium, but it is what it is. C'est la vie. So I just want to talk about some of the more interesting aspects of equilibrium that maybe you haven't talked about in your other classes. Okay, so so you can see here. I'm going to start by talking about the Gibbs energy minimum, but first let's just go back to basics with equilibrium. So suppose we have A in equilibrium with B. Okay, so we know from our Gen Chem days that I can write the equilibrium constant as of this thing as the concentration of B over the concentration of A, right, for this simple reaction. But how do I get that? Where does that come from? Okay. Well, I'm going to introduce a new quantity called extent of reaction. And this crazy little letter that you see right here, can I even make it? Yeah, whatever this thing is. So this is the extent of reaction, and that is the Greek letter Z. I think I did a terrible job drawing Z. It's the hardest damn Greek letter to draw. So anyways, what is that thing? Well, if I look at this equilibrium and I look at the change in the number of moles of A, D in A, ha ha ha, this is equivalent to negative dz. I think that's how I do it, okay? And the negative because it's a reactant. So the reactant will decay. Its concentration will decrease over the extent of this reaction, over time, okay? So we can also therefore say later, I don't want any results, remind me tomorrow. I can also say then that D in B is going to be positive dz. And the reason why these are equal and opposite is because of the stoichiometry, because I can see A and B are 1 to 1. Okay. So now let's see here. If we establish then this situation, I can write delta G of the reaction, and I'm going to put standard Gibbs free energy of the reaction is then going to be equal to the partial of G by the partial of Z, all at constant P and T. And we don't hold the moles constant, right? Because that's that dz. The moles change. That's what makes it a chemical reaction. Okay. So now if I write out the total differential for G, dg is then of course mu A, the chemical potential, times D in A. So we established this in our chapter 5, times mu B times D in B. And substituting this new parameter, this Z, extent of reaction, we know that's going to be negative mu A times dz, so the negative sign got absorbed there, plus mu B times dz, okay? And now if I collect like terms here and do a little bit of algebra, then I get that this is mu B minus mu A times dz, okay? So then thus I can say that the partial of G by the partial of Z at constant P and T equals mu B minus mu A, okay? Right, because now I'm moving this dz over to the side, right? dg equals this, and if I divide that out, then I get that partial. And I'm going to now specifically define that as delta G of reaction. And of course, I put the standard here, noting that if I make these standard and these standard, so the 298.15 K value, then I'll have those standard values. Okay? So how does this lead to the Gibbs free energy minimum? Well, we arrive at a couple different situations here, 3 different situations. One in which mu A is greater than mu B. One in which mu A is less than mu B. And of course, one in which mu A equals mu B. So what does this all mean for equilibrium? Well, if we look at my equation right here, okay, in the case that the chemical potential of A is greater than the chemical potential of B, okay, that means that free energy of reaction will be less than 0, which you can actually see right here. So if now I plot free energy versus extent of reaction, and I'm in this situation where mu A is greater than mu B, look, the free energy is negative, and that means we spontaneously proceed down through the reaction, okay? We then get to a point now, as indicated by the graph, where there's 0 slope. And so you can see that corresponds to this case right here. And when the two chemical potentials are equal, we call that equilibrium, okay? So the delta G is 0, and we recognize that's a special case that we call equilibrium, okay? And that's when the two chemical potentials are equal. So in all intents and purposes, the reaction has stopped, right? The reaction is really done. And so we would have some equilibrium amount of B and A that would give us that equilibrium constant, okay? Right? Based on this extent of reaction, I know that I could then compute the amount of A and the amount of B, recognizing that I would have to know the initial amount of A and the initial amount of B if I had any. And of course, when we have mu A is less than mu B, then that quantity will be greater than 0, which as you can see is right here, which means the reaction will not spontaneously proceed any further. However, if we were to start the reaction with B, right? So remember your equilibrium and how it's very much related to reactions that can be reversible. So let's suppose I started with all B. Well, then if I'm starting with all B, we actually recognize that it would be spontaneous in this direction, in the reverse direction. And I would still end up at this equilibrium point, okay? So that is how the Gibbs energy is connected to equilibrium and the chemical potentials, okay? The Gibbs free energy minimum. So I'm going to use, as we always do in this class, ideal gases to establish our first example. And then, you know, like I would spend a lot more time establishing other examples based off this, but I'm just going to show you this ideal gas equilibrium example because of time, okay? So we know delta G reaction equals mu B minus mu A, okay? And if now I expand on these, okay, so notice I'm not putting these as standard, okay? This is just the free energy of the reaction. So if I were to expand on mu A and mu B, then I recognize that mu B can be written as the standard reference state plus RT. So let's go back to establishing that this is A and B in equilibrium. Oh, actually, let me write those as gases. So A as an ideal gas is in equilibrium with B as an ideal gas, okay? So mu B standard, so the standard value plus RT times the natural log of the vapor pressure of B, or the partial pressure, I should say, divided by standard pressure. Okay, so this is how we make our adjustments when we're in non-standard conditions, all right? And of course, now this is minus A, so the standard chemical potential of A plus RT times natural log of the partial pressure of A over standard pressure. And what I want you to recognize based on this last lecture now, we can see this quantity right here, this is actually the activity of B, and this is the activity of A. Activities. So as we're going to find out, activities are strongly connected to equilibrium. Okay? So now I'm going to collect some like terms. I'm going to remember that what I established in that last slide is my standard free energy can be related to the standard chemical potentials like so. And so now what I can write is the delta G of reaction under non-standard conditions, so under any condition, and that is going to equal now, collecting like terms, mu B standard minus mu A standard. That's the same as the standard free energy of reaction. Okay. And then now I've got plus RT natural log. And so technically what all of this makes here, I'm going to put this in brackets. I have now, this will be PB over P standard divided by PA over P standard. So the ratio of activities, okay? The ratio of activities. So let's write that. Let's simplify that. So now that all equals delta G reaction plus RT natural log of the activity of B divided by the activity of A, okay? And so if we now look at this, we're poised to say here, to start adding some familiarity to this, I'm going to simplify this reaction or this expression even further and say that's RT times the natural log of the quantity Q, where Q is my reaction quotient. I can't spell quotient. Sure. Reaction quotient. Okay. And we know that the reaction quotient, we can say now, we can see that that is the activity of A over the activity of B. Okay. From your Gen Chem days, we established that Q, the reaction quotient, is actually the partial pressure of B over the partial pressure of A. And if now you inspect this ratio, right, P naught, that value right there, that's just standard pressure. That's just 1 bar, okay? So as you can see, if I ratio the partial pressures or if I ratio the activities, it's the same thing, all right? And so now the big rub here, this is for initial conditions, okay? So what happens at equilibrium? Well, what happens at equilibrium, delta G is 0, all right? And notice here it's not standard delta G, it's just the delta G. So that means now when I make this 0, all of this equals delta free energy of reaction plus RT, and now that becomes natural log of K. All right? And so K is still a ratio of activities, but now those are the ratio of activities at equilibrium. All right? So hopefully this is all somewhat familiar to you. Hopefully you all remember this stuff. And so why is this ideal gas equilibria? Well, it's ideal gas equilibria because of how I'm able to just say the partial pressure of B over the standard pressure is its activity, which can be directly related to the number of moles. So that's what makes this come from ideal gas equilibrium, okay? Okay, so now once again, so we've established the following. So we established when the total free energy is 0, okay, then I still have the standard free energy of reaction plus RT natural log of K. All right? And so if I rearrange here and do some algebra, so subtract delta G over, divide by RT, take the E of both sides, so I'm just going to write that result directly, then we get that the equilibrium constant K is the exponential of negative delta G standard of reaction divided by RT. And I want you to inspect this equation for just a minute. Does the functional form of this look familiar to you? The answer should be yes. This looks like our Boltzmann distribution, right? It's some exponential of, an energy. In this case, it's free energy, but it's still energy divided by RT. Awesome. I told you guys we would see this partition, function everywhere in chemistry. And here we see it with the equilibrium constant, okay? So now what's going on with this free energy right here that we set equal to 0, okay? So that's really this term right here, okay, or this y scale. And so what do I have going on here? Well, without mixing, this line really gives us the standard free energy of reaction. So in other words, at this point right here, that's the free energy initial. So we'll say that's the standard free energy of the reactants, right? And then this point right here, that's the standard free energy of the products, okay? So you can see this gives us a spontaneous reaction, right? Spontaneous going that way. So let me write that, right? So we recall that standard free energy of the reaction is just the sum of the final free energy. So we know that that's the free energy of the products minus the sum of the initial free energy. So that's the free energy of the reactants. But look, all this is, because it's a state function, it's just this minus this. So that just gives us a straight line. So where does this curvature come from? Well, it comes from mixing. And where do we get the mixing? Well, this equation right here, we derived in chapter 5 from mixing two quantities. So I'll write that full thing down. And I'm just going to be consistent with the book here. It writes the delta G R. I think it went delta RG is standard free energy, okay, plus RT. And now I'm going to make that natural log Q. All right. So really this expression, this delta G of reaction plus this RT natural log Q, that comes from mixing A and B together, okay? And if we recall, so if I dropped out this delta G reaction, then I get this, that minimum delta G, which for anything, and so this comes from ideal gas, okay? We actually predicted that the minimum occurs at a mole fraction of 0.5. So that will be true for any simple equilibrium, that the free energy minimizes at 0.5 mole and 0.5 mole of each, or 0.5 mole fraction of each, okay? So there's a really important role in mixing with equilibria, because now when I add those together, so in other words, when I add this red line to this blue line, the result I get is this free energy expression, which predicts a minimum, somewhere right here, right? This is where I establish my equilibrium mixture, okay? And so what we might guess then is if Q, or I should say if our reaction is complicated, right? I'll write down that we have this simple reaction right here, okay? Then that establishes that 50-50 mixture. So obviously if my reaction is more complicated with that, if there's more dynamic stuff going on with the stoichiometric coefficients, I won't have a 50-50 minimized mixing, and thus the position of equilibrium will be very different. And so not only does that matter for mixing, but that also matters for this slope right here. So the reaction energetics also predict where my equilibrium mixture should be, okay? Fantastic. So I think that's a pretty good amount of stuff. So moving on now. So we're ready to establish the actual definition of a chemical equilibrium expression. And so first I will establish the mathematical definition of a chemical reaction, which goes as the following. And I'm just using consistent nomenclature from the book. So this is the mathematical definition of a chemical reaction, okay? So J, that's chemical species J. Okay, so that's chemical identity. This is the stoichiometric coefficient that you use to balance the reaction. And the sum of all of these should equal 0. So that's saying the reaction has to be balanced. So for example, if I have a reaction that says 2A plus B goes to 3C plus D, then first I have to establish all of my stoichiometric coefficients. So nu A equals -2. So we put a negative sign for reactants. Okay? Technically, mu B is -1, mu C is +3, and mu D is +1. Okay? So now if I put that together, that's going to say 0 equals -2A minus B plus 3C plus D. And if I rearrange this, you can see it's going to be 2A plus B equals 3C plus D. So that's how we establish a mathematical definition of a chemical reaction. Fantastic. Okay? So then now, what we recognize then, based on that last thing that we just developed, we see that the reaction quotient Q, so in that simple equilibrium expression, we established that Q should be the activity of B over the activity of A. So I can use that to establish a mathematical description of an equilibrium expression, okay? Which goes as the following. The reaction quotient Q equals big capital pi, okay, sub J. So if this is the Greek letter sigma, which equals a sum, this is the Greek letter pi, capital Pi, which equals product. I'm not sure if you knew that or not. Sum, sigma, or sigma gives us the summation. Capital Pi is a symbol for product. Okay? And so our Q becomes A, the activity of species J, raised to its stoichiometric coefficient. Okay? For initial activities, okay, so I'm going to say AJI, or we know that K equals big capital Pi, AJ, and I'll say equilibrium raised to the mu J power. This is actually the law of mass action. Law of mass action. This is actually it. That's how you establish the equilibrium expressions. Okay? So let's write all of that down now. Okay? So if I'm doing this, let's write it for, so it works either way for Q or K. It just depends on if you're talking about your initial activities or your equilibrium activities. So I'll just write this down for K. And here's how this product works. And we'll use the same example up here. Okay? So that's going to be the activity of species A raised to its stoichiometric coefficient raised to the -2 power. And now it's not a sum, rather it's a product. So times the activity of B raised to its stoichiometric coefficient times the activity of C raised to its stoichiometric coefficient, which is just +3 now, times the activity of D. And of course, that's going to be raised to the power of 1. All right, great. So now if I simplify that expression, we know it's going to be the activity of C cubed times the activity of D raised to the first power divided by the activity of A squared divided by the activity of B. And wonderful, that's what you would have come up with, hopefully, in Chem 109. Of course, in Chem 109, we would have established this really as the partial pressure of C cubed times the partial pressure of D to the first power times the partial pressure of A squared times the partial pressure of B to the first power. That's how you would have come up with this in Gen Chem, okay? Which is mostly correct. But hopefully, if you recall from the last exercise, right, where we talked about ionic activity in particular, using concentrations as opposed to activities is only approximate. So we actually have to use activity as the most correct form here, okay? And so now, just to kind of go through like one example here, let's say N2 gas. So an old familiar gas here, the Haber-Bosch reaction to make ammonia to NH3 gas, okay? And so we know that K would be the activity of ammonia squared divided by the activity of nitrogen times the activity of hydrogen cubed. And if I want to be really, really correct and precise on this thing, then I can write it as the following. I can say that's the partial pressure of ammonia divided by standard pressure, all squared, divided by the partial pressure of nitrogen divided by the standard pressure, times the partial pressure of hydrogen divided by the standard pressure, all cubed. And when I do that, that's how I arrive at your good old-fashioned Gen Chem equilibrium expression that you would have just said is based off of the partial pressures, okay? But now I'm going to have, look, 1 over P naught squared divided by 1 over P times 1 over P naught cubed, okay? And so when I do all of that, okay, so that gives me a, can I come up with this? So I'm going to have times 1 over P squared times 1 over P naught times 1 over P naught cubed, okay? And all of this, so that becomes 1 over P squared divided by 1 over P to the 4th power, which actually just equals P squared. Okay, so do the algebra to prove it. So what about the units now? Well, this is going to be partial pressure of ammonia squared gives me a bar squared divided by pressure of nitrogen gives me 1 bar times the pressure of hydrogen cubed is a bar cubed. But now look, all of that, the standard 1 bar pressure, that all became a bar squared. And let's inspect this for 1 minute. I've got a bar squared times a bar squared, that's bar to the 4th power, divided by bar to the 4th power. So this is why equilibrium expressions are actually unitless. Maybe that bugged the heck out of you in Chem 109. We told you, oh, they're just unitless. But like if you use this chunk, you can see that's clearly not going to be unitless. But because because equilibrium is technically based off of activity, it does become unitless, okay? And so, of course, we could also do this. What's coming up next? We could also, so I just did this for partial pressures. So technically that would make this Kp, if you remember. Well, there's all sorts of various equilibrium expressions, and I'm not going to spend a whole lot of time going through those, but I'll just give you one example. So Kc, if we were doing this in terms of the molarities, all right, then we could write the law of mass action as the following. The product of all species J, which is going to be times the activity of J raised to the new J power. Well, I now know that I can write activity in terms of partial pressures, but I could also write activity in terms of concentrations. And so that goes as the following. Pi J times the molarity of J as expressed in a bracket divided by C standard, all raised to the stoichiometric coefficient, where C standard is exactly 1 mole per liter. So then, in other words, I can still write this Kc as write the concentration of ammonia in moles per liter squared divided by the concentration of nitrogen divided by the concentration of hydrogen all cubed. But what we also recognize in the same way, there's also going to be times this other factor, this C standard concentration, all squared. And that's not going to change the numbers at all because that's just 1 mole per liter, but it does establish the unitless equilibrium concentration in terms of concentrations, okay? So we could spend like a whole day going through various examples, but again, I just want to kind of establish what's important, okay? So moving on, the molecular interpretation of equilibrium constants. So what this is related to, the only thing I'm going to say about this is how equilibrium constants can be related to the thermodynamic potentials, okay? So we know now that K equals the exponential of negative, the standard free energy of the reaction, divided by RT, okay? We can write that the standard free energy of reaction is equal to the following: delta H of reaction minus T delta S of reaction. And so I can substitute that into K. And this would have been an exercise that we would have played with more in Igor with some data fitting. But you guys are probably sick of data fitting, so we're going to move on. Okay? So now I can rewrite this expression putting in this, plugging this into delta G, and I get the following: exponential of the negative delta H divided by RT times the exponential of, and this is going to be delta S of reaction, just divided by R because I have that T times delta S. All right? And so now what we can get out of this actually through graphical analysis, if I take the natural log of both sides, then I get the natural log of K is equal to the negative delta H of reaction divided by RT. Let's see, and then that's plus delta S, oops, I said S, but I wrote G, plus delta S of reaction divided by R. And of course, if I were to do a graph of the natural log of K versus 1 over T, this would actually help me establish if a reaction is endothermic or exothermic, okay? Because if a reaction is endothermic, I have a negative sign right there, so I would see a negative slope from this. Okay, so this is for delta H greater than 0. So that would help me establish, like molecularly, what's happening with the reaction. Is it endothermic or exothermic? And if I see that a reaction is exothermic, I will actually get a positive slope out of this thing. Delta H is negative because negative negative makes a positive, right? Okay. Fantastic. And so what this means is when you have, so in terms of equilibrium, what this favors now, okay? So if I go back to this expression right here, talking about this expression, we also remember from our Gen Chem, what does K greater than 1 mean and what does K less than 1 mean? Hopefully you remember this, but K greater than 1, we know favors products, and K less than 1 favors reactants. So what can we say about the delta H and the delta S in light of these two conditions? Okay. Well, if we have a delta H greater than 0, what does all of that give us? Well, a delta H greater than 0 means that this exponential is going to be negative, and the exponential of a negative quantity is less than 1. So a delta H that's greater than 0 has a tendency to favor reactants. Okay? Similarly, if the delta H is less than 0, So we have a negative times a negative, which gives me a positive, and the exponential of a positive number gives me a number that's greater than 1. So with exothermic reactions, there's a tendency to favor products. Now, of course, we have to consider what's going on with delta S, right? And so what we should establish for all delta S of reaction greater than 0, so in other words, for all spontaneous reactions, okay, will favor products, right? Because if a reaction is spontaneous, its delta S is greater than 0. That's the exponential of a positive term. The exponential of a positive term gives me something greater than 1. And when K is greater than 1, it favors products, okay? And so now what's a really interesting case here is when you have an endothermic reaction that's spontaneous. It can happen, okay? And that really, we have to now look at what's going on with the temperature. So think about this now. Let's back this up here. So I'm just going to try to describe this conceptually, okay? If we have a spontaneous reaction, we know that that's favoring products. But what if that reaction is endothermic? That's going to favor reactants. So what this means now is there's a competition between these two chunks. One chunk will be greater than 1, the other chunk will be less than 1, and when we multiply them together, that's going to tell us what won. Did the entropy win or did the enthalpy win? And as it turns out, the temperature of that situation is critically important. So in other words, if the temperature is sufficiently large, I think I ran out of slides here, but let's add another slide. If T is sufficiently, assuming I can spell, and let's go back to this expression, right? K equals the exponential of negative delta H over RT times the exponential of delta S over R, okay? If T is sufficiently large, then if you think about it, what that means is this term will be small. So even though it might be endothermic, which might favor reactants, if T is sufficiently large, there's enough thermal energy to still drive that reaction spontaneously on to products, okay? So what's also cool about this, what this also establishes, so now we'll say if T is sufficiently large, endothermic reactions can favor products. So what about the other case? What about an exothermic reaction? Well then, if T is sufficiently, I can't spell, whatever that says. If T is sufficiently small, then an exothermic reaction will also favor products. So this is actually why exothermic reactions are more efficient when it is colder. And the reason for that is because now you have a negative in this term, so that gives you a positive. But when T is small, it's going to make this number really big. And the exponential of a really big number is an even bigger number, which gives you a humongous K favoring products, okay? And so now I'm looking at the time. I've been talking for 40 minutes now. And so what this is really establishing is Le Chartier's principle. Okay, so we can talk about changes in pressure and changes of amounts and the Chartier's principle. I hope that's more or less a review for you. I'm not going to talk about this any because I don't want to take up too much more time. So review your basics on the Chartier's principle if you need to. Okay. But really what I was getting into there is the changes in temperature with Le Chartier's principle. Okay. And so again, what we establish here is the necessity, the dependence of temperature on these spontaneous reactions, okay? And so, for example, if I have an exothermic reaction, as indicated right here, if I increase the temperature, it's like I'm adding more products, right? And that's going to make the reaction favor the reactants, right? Okay, so that's why if I decrease the temperature, if I have a low temperature in an exothermic reaction, we know that it's going to favor products, okay? So, and similarly, in an endothermic reaction, we know energy is a required reactant. So this is where if I have a high temperature, if I increase the temperature, I can actually drive this reaction to products, okay? Even though it might be endothermic, I can still make it proceed spontaneously if I drive up the temperature high enough, and that makes good sense. And of course, similarly, if I decrease T on an endothermic reaction, then I'm going to be, pushing my equilibrium to the reactants, okay? And so all of this is established, so we can then recognize that the only thing that actually changes the equilibrium constant is temperature through this equation. K equals the exponential of negative delta G of reaction divided by RT. So we recognize that K is dependent upon what the temperature is. So with changes in pressure or changes in amounts or changes in volumes, I'm not going to go through this, but it does not change the equilibrium constant. Does not change K. But we do know that changing amounts, which is more or less the same as changing pressure or changing volume, can shift equilibrium to reactants or products, okay? And if you had me in Chem 110, we spent a glorious, hideous amount of time discussing all of this stuff, okay? So that's really all I want to say about equilibrium. I actually want to say a lot more, but I'm trying to get us to come back, get back in time with the course. So hopefully this was a little bit new for you. Hopefully you learned a few things about equilibrium that you didn't know before. That's kind of my main goal here. You talk about equilibrium in every damn chemistry class. So hopefully I was able to hit on some things that were new for you. Okay, folks, so this wraps up thermo. We're done with thermo. Yes, we're going to move on to kinetics. I'm going to start recording kinetics for week 11. Okay, so make sure you wrap up everything in thermo and be ready for the super quiz on Friday of next week. That's Friday, November 6th. Okay, folks, hasta luego.